So, okay. So until now, we saw that the mean squared value of the noise from R on is KT by C. So, which is basically independent of the R on itself. So, because even though if we say that the SVN or the spectral noise density increases with R on, but the bandwidth of low pass filter which it is being passed through decreases with R on. So SVN is passed through that bandwidth. So the effect of R on is getting cancelled, and the mean square value is independent of R on. So this is what we saw in the end of previous video. So let's say when we open the switch, there is some noise voltage which is sampled on the capacitor. In that we also have our input voltage which is sampled, right? So the noise voltage is just the addition to the input voltage, and the next time when we again close and when we track and we again open the switch for the next sample, now we have another value of noise. Thus the noise which is sampled in each cycle is not correlated, or it is uncorrelated. So what am I basically saying is we close the switch at n equals to 0. So let's say first cycle. So when I close the switch, we have, and the input is 0. Basically over here, we are just analyzing the noise. So we have the source due to the noise, we have resistor, the switch is closed. So what happens? The capacitor gets charged. Now when the switch is opened, the noise is sampled on the capacitor. So our V noise is basically Vn out for the 0th sample. So the noise sampled on the capacitor when the switch is opened is basically Vn out. And when we again close the switch for the next cycle, then the capacitor will again be sampled with the noise. And again, when we open, we again have some sample of noise on the capacitor, and the noise sampled on C when switch is opened again is basically Vn out of 1. So we are saying that this quantity Vn of 0 and this quantity Vn of 1 are totally uncorrelated, right? So why? So basically the clock period is chosen much higher than the RC time constant, because we are integrated in high tracking bandwidth. So we need our bandwidth of tracking to be very high or very large. So if we want to be able to track a signal with a frequency as large as fs by 2, then the tracking bandwidth must be much higher than fs by 2. So what does this means? So it means that the RC time constant must be much smaller than the clock period itself. So rethink about it, go through it once again. You'll be able to catch it very nicely. So now, if RC time constant is very, very small, then the sampled noise on C will quickly discharge, because that's what the time it takes for a capacitor to charge or discharge, right? So when we open the circuit, or when we open the switch basically, so then if RC time constant is very, very less, so this means that the sample noise on capacitor will basically quickly discharge, which means at the end of the next cycle, previous voltage has completely discharged, and now the voltage held on C is basically a largely function of only the input waveform at that particular cycle. So the previous noise was completely discharged. So now whatever the sample which is held by the capacitor is only the voltage which is at that particular time, or the signal at that particular cycle. And also, as the noise is white and random, it is uncorrelated period to period or cycle to cycle. So thus there almost lies no correlation between successive samples of the output when it comes to noise. So yeah, this is the fact. And so basically, if we choose the capacitor value to be very small, then the noise effect will be really significant because it's based on KT by C. So if C is very small, then KT by C will be really significant. But at the same time, if we choose capacitor value to be too large, then the RC time constant will be high. But as we said, we need the time constant to be less. So is there any way to choose the value of capacitor? So how do we choose the value of capacitor? So the base what we come up to is, you guys are aware about the idea of quantizing the amplitude now, because now we are using a sampler, so we are using a switch. So now the time is sampled. Now we have to sample the amplitude also, right? So the amplitude should be quantized. And when it comes to the quantization of amplitude, what we do is basically we quantize it in steps. So yesterday I shared you the picture of going from sampled time to quantized amplitude. So that means that there is a step size of the quantizer, right? So the step size of the quantizer is already given, and let's say we have ideal quantizer following the capacitor. So after the sampler, we have the quantizer for amplitude quantization. So we will make sure that the RMS value or the root mean squared value of noise is smaller than the step size of the quantizer itself. So what do I mean by this is basically, let's say in the uh, sampled domain, you have your sample like this, right? You have a sample like this. So when it comes to this domain, so these are your steps. Let's say these are your steps. So this will lie in this step, right? So then for this particular sample, we have like this. This is the plot for quantized value. So then what we say, so basically this is the value of that sample, but due to the noise which will sit on this V in, the noise can go up or down for a little value. So then what we say that it might shift the quantization, right? Like it might shift the step. So we say that the length of this step should be really greater than this noise. So basically, this noise cannot shift from one step to another due to uh, and give us the error. So that's what I mean. So the idea behind this argument is that anyway we are going to lose some information after we quantize the amplitude levels. So we need to make sure that the noise that we add to the sampling is smaller than the step size we use for the quantization. So basically, root mean square value of the noise is root kt by c should be really smaller than the step size. And it's always easier to build a quantization step of larger value, or it is harder to build a quantization step which has very smaller value. But then again, if the value of the quantization step is higher, then the error due to quantization of amplitude is again higher. But anyway, we have thermal noise error, right? So we will make step size larger than the error due to the noise, so that it will not give us the error in quantization. So commonly, the RMS value of thermal noise is chosen as 1/4 of the quantization step. And this is not the rule, but usually it's done. So as far as the resolution is concerned, we make the value of C significantly high in order to make KT by C minimum, in order to achieve smaller and smaller quantization step, because the smaller the quantization step, the higher the resolution is. So then from here we somewhat get an idea that what the value of C should be. So now let's say if we have a peak signal amplitude of A, then we can quantify the signal to noise ratio after sample and hold as uh, SNR equals to the signal power divided by the noise power, which is basically the signal power when it is sinusoidal input is amplitude square by 2, and the noise power is KT by C. So from this value, we have our signal to noise ratio, and based on what kind of signal to noise ratio we want, we can design the value of capacitor. So now we should try and figure out how to realize this using a device that we already know. So now we know that how to design a sampler or what things we require while designing a sampler. So while designing sample and hold, we have to uh, we have to design it on a circuit level using our components which we know. So the best choice for making a switch is a MOSFET. So it's a MOS transistor, and this is the basics of MOS transistor. Like we have drain, source, on gate. The board is usually connected to the ground. It's not accessible until and unless it is a N-well as NMOS. So N-well MOSFET. So in N-well MOSFET, you can also use the effect of body to manipulate your MOSFET. But as of now, it's, let's say the body is at ground. So if we want the MOSFET to work as a switch, we want it to work in a triode or the linear region. So basically, when we are in the track phase, when the switch is closed, the MOSFET should act in a triode region. And when the switch is open or we are in a hold phase, so the MOSFET is off. So what happens in triode region of a MOSFET? So we'll just go through the basics of MOSFETs. So in the triode region of the MOSFET, the VGS is greater than VT. So VT is the threshold voltage for a MOSFET to start or switch on, and the VGS, so basically the voltage at gate and the voltage at source. So voltage at gate minus voltage at source should be greater than the threshold voltage itself, and the voltage at drain and voltage at source, so VDS, should be less than VGS minus VT. Also, VT is also a function of VSB, but as of now, we will neglect the variation in VT because it's very small, and the current in the triode region is basically given by, this is a constant value, K times VGS minus VT times VDS minus of alpha VDS square by 2. But over here, this term can be neglected because we will be working in such a small VGS that we can ignore this term. And this is basically the variation of VT along the channel N, and it is typically 1.1 or 1.2. So we will ignore this and we'll uh, go ahead. So when we go ahead, we get the resistance offered due to the MOSFET, or the resistance offered due to the switch, basically equals to this value. So this basically comes from Ohm's law, V equals to IR. So R is V by I. So then we use our MOSFET as a switch in our circuit where we have the input signal, we have our capacitor, we take our V out from here, and we put our switch, or we put our MOSFET over here. So this is gate, this is source, and this is drain. So we assume that all circuit operates between 0 and VDD. So from ground and the highest voltage provided. So let's take a common average voltage, which is VCM. Basically, this is common mode, which is VDD by 2, and this is at DC. So our VDD is at DC. Our ground is at 0 volts, so DC. So VCM is also at DC, and whatever analog signals we will be having. So let's say this is VCM. So our analog signals will basically ride on this VCM. So our input is also basically VCM plus Vn. Vn is A sine omega t. So again, we know, we are aware about this circuit. So we are just using MOSFET as a switch over here. So when we are in the track phase, which is basically when the switch is on, our VG, this VG is connected to the highest possible potential of that circuit, which is VDD. And when the switch is off, it is connected to ground. So we have our clock cycle where we have track and hold, and highest value is, so basically the MOSFET, gate of the MOSFET voltage, so potential at the gate of the MOSFET will go by this cycle, which is ground and VDD. And we have, when it is VDD, we are in the track phase. When it is ground, we are in a hold phase. So also, this is our input signal, which is riding on VCM with amplitude of A and minus A. So the MOSFET's offered resistance depends upon, this is a constant. So it depends upon the voltage, which is inversely proportional. So if we plot the input, so it is riding on VCM. So in the track phase, VG is VDD, but what is VS? What is V source? So V source is looking at the input, or basically the input is looking at the V source. So voltage at source will be A sin omega t plus VCM. So then what will be VGS? Because the resistance is dependent on VGS. We are saying that VT as of now is constant. So Vs is this. So VGS is basically VG minus Vs. And when we take the difference, we have VDD minus VCM plus A sin omega t, where our where our VCM is VDD by 2. So we put the value of VCM as VDD by 2, then we get VDD by 2 minus A sin omega t as the value of VGS. So now we realize the resistance. So when the resistance due to the MOSFET is chosen to be sufficiently small, because it's a switch, so it should offer sufficiently small resistance. So then the voltage drop across the MOSFET should be very small as compared to the voltage drop across the capacitor, because we have only two elements. So the total voltage drop will be voltage drop this plus voltage drop of this. So if we say this is very small, so all the voltage should be being dropped across the capacitor. That's what we want. We want the input voltage, input signal to be sampled on the capacitor itself. So we know R on is inversely proportional to VGS minus VT. And as the input signal keeps changing, the gate, so this signals is not constant, right? This input signal keeps changing by the value between VCM minus A and VCM plus A. So the source terminal is exposed to a varying input. And if the input becomes very high, let's say, then VGS decreases. How? So VGS is basically dependent on the input. So if input goes up, VGS goes down. So if input becomes high, VGS becomes low, and thus the value of VGS minus VT also goes down. And if the value of VGS minus VT goes down, basically the resistance offered by the switch goes up. So it might happen that if the input becomes too high, then VGS minus VT might go below zero, and basically VGS might go below VT. And if VGS is below VT, then it will turn off. So it might happen that when input is too high, the switch might, or the MOSFET might turn off. And also when input is at its negative half, so the voltage is going down. So when it is in negative half of the cycle, then VGS increases, resulting in RC time constant being reduced. So this non-linearity results in harmonic distortion. So our resistance is not constant. It depends on the input voltage, and it also depends it on not on linear basis, but it is non-linear. So when we have non-linear resistor R on, so we have an input, right, like this. So the positive half of the input, the R on increases. So if the R on increases, then 1 upon RC decreases. So the bandwidth decreases, and vice versa. So the resistor is now a function of the amplitude of input voltage, which is non-linear. When the amplitude goes up, then the resistance goes up, and the bandwidth of the RC network basically reduces. And what does it means? So if the bandwidth reduces, the delay between the input and the output signal will increase, whereas the resistance decreases when the amplitude goes down, and thus the phase difference between output and input signal reduces. So one can what one can do, so one can model the resistance R on to depend on the input voltage using a polynomial. So we can model it mathematically using polynomials. So what we have basically over here is under a nominal conditions when A is zero basically, or let's say not zero, but voltage drop across the switch is very small. So what happens? Voltage drop across the capacitor is basically nearly equal to the input voltage. So whatever we have voltage at input, the voltage drop over here is very small. So everything which is dropping across the capacitor. So we assume that V out is nothing but VCM plus A sine omega t roughly. So then the current through the capacitor is C dV by dt. We know the current through the capacitor is C dV dt, C dV by dt. So then when we do the dV by dt of input, what we get? We get Ca omega cos omega t. So also the switch has got some finite resistance, and the current flowing the switch will be again roughly Ca omega cos omega t. So now if R on was linear with the voltage, so the voltage drop across R on would have been linear. So let's say if the voltage drop across the resistor is Vx, which is basically if it would have been linear, so the value would have been R on times the current V equals to I R. So assuming that the drop across R on is very small as compared to the amplitude of the input signal, so or basically the amplitude of waveform across capacitor, then our voltage across resistance would have been this equation, but unfortunately R1 is a function of input amplitude. So having a large tracking bandwidth, so we need a large tracking bandwidth, right, to get all of the signals sampled on the capacitor. So having a large tracking bandwidth physically means that the drop across the switch, so the drop across the switch should be much smaller as compared to the input, which means that the output amplitude will be roughly as same as the input amplitude. But unfortunately, what happens is R1 is a function of input amplitude. And let's say, let's denote it as R of V in. So basically, R of V in using polynomials can be given mathematically as R on itself, but it also have the variation, let's say R1 times V in, R2 times V in square, R3 times V in Q, so and so on. So that's how we give the nonlinear relation. So the first two terms over here are good enough to moderate this equation accurately, or basically to go like get an idea of the effect of non-linearity on the waveforms. So let's say RV in is this value. So then the voltage drop across the switch is simply C dV by dt. So the current times the resistance. So this is the resistance, this is the current. So, but C dV in by dt we have approximated, but actually the voltage across capacitor is V out, not V in, but we have approximated that the voltage drop over here is very less. So all the voltage samples on the capacitor, and that's how we have approximated that it is C dV in by dt. So this is the current, this is the resistance. So we have voltage drop across the switch who has the value this much. So for a sinusoidal V in, let's say V in is A sine omega t. So the Vx will be nothing but Ca omega n cos omega n t. So this quantity is basically dV in by dt when V in is A sine omega t, and this C comes along like this over here. So this entity is nothing but the current times the resistor. So now I would like if you guys solve this complete value. I have solved it just try to understand. And then when we understand, then we'll talk about the intuitions, that what does this huge equation of the voltage drop tells us about the switch. So you can refer to these things and try to make an intuitive sense out of this equation. So that's all for this video. In the next video, we'll talk about what this equations tells us. So what are the intuitions behind it? So we'll talk more about it. So that's all for this video. Thank you. So if you have any doubts, please go ahead.
Thank you. Everything was clear.
Oh, really? That's great. So like I talked about a few things about MOSFET. So you can go through that video. You'll easily understand. Or
Yes,
maybe,
exactly. 21.
yeah, if
Yeah,
you
no.
it might happen that in the starting of that video, I might say that we started with the idea of MOSFETs in previous video. So then just go to previous video and look for the end, like end 4 to 5 minutes, where I've discussed or started to discuss about MOSFET, and then watch next video. Like you understood, right? What?
Yes, yes. Yes,
Yeah.
sure. Don't worry about it. Thank you.
Yes. So, but it's super basic. So you can understand it in 15 minutes. You can also Google it, you'll understand in single
Yeah,
video.
okay.
That's all for this video. What about Sneha?
Yeah, Rishi, I will go through this one more time.
Yeah,
Then
perfect.
I'll get back to you. Yeah.
Yeah, perfect. But you understood what is happening over here, right?
Yeah, I got the picture of what you are explaining.